Watch this. We just killed a pod. And there it is, a new one. Different name, only a few seconds old, already running. We didn't create it, no script ran, no CI pipeline kicked off. Something inside Kubernetes noticed a pod was missing and replaced it, on its own, within seconds. What brought it back? What noticed it was gone? How did it know what to replace it with and where to put the new one? That's what this video is about. We're going to look at the system underneath, the design pattern that drives all of Kubernetes, and the components that make pods, services, deployments, and how these actually work. Before Kubernetes, most of us had a simple mental model for deployment. You have code, you have a server. You put the code on the server. Maybe you SSH in, pull from Git, restart a process. Maybe you have a script that does it. The point is, you are the operator. You decide what runs where. Kubernetes inverts this completely, and many people try to use Kubernetes with the same old thinking process. They think of it as a tool that deploys containers to servers. But it's something fundamentally different. Kubernetes is a declarative state management system for infrastructure. You don't tell Kubernetes how to do things. You tell it what you want to be true. And then it continuously works to make reality match your description. So let's talk about the mechanism that makes this work. This is probably the most important concept in Kubernetes, and it's one that often gets buried under all the YAML and tooling. It's called a control loop, or a reconciliation loop, and it works like this. Step 1, observe the current state of the world. Step 2, compare it to the desired state, the state you declared. Step 3, if they don't match, take action to close the gap. Then repeat, forever. It's exactly like a thermostat. You set the desired temperature. The system checks the current temperature. If they don't match, it acts. The room reaches 72, the heater turns off. Then someone opens a window. Temperature drops. The heater turns back on. It doesn't execute a one-time script. It continuously reconciles. This is how Kubernetes works. Not one control loop, dozens of them, all running in parallel, each responsible for one narrow concern. There's a controller watching your replica sets. When a replica set says, there should be 3 pods, that controller checks how many actually exist and creates or deletes pods until reality matches your description. There's a separate controller watching deployments. Its job is to manage replica sets when you roll out a new version. There's another controller watching nodes. If a node goes dark, that controller notices and marks its pods for rescheduling. There's one managing endpoints for services, another handling persistent volume claims. Each one runs independently. Each one follows the same pattern: observe, diff, act. And none of them know about each other. They only watch their own objects and reconcile their slice of the world. And they all coordinate through a single source of truth, a distributed key value store called etcd, with the API server sitting in front of it. Both your desired state and the actual reported state live there. When a controller needs to check what did the user ask for and what's actually running, both answers come from the same place through the API server. When you run kubectl apply, you're not deploying anything. You're writing your desired state into etcd through the API server. The controllers notice, and they do the rest. This is why Kubernetes is self-healing. It's not a feature that was bolted on. It's a natural consequence of the architecture. If a pod crashes and gets evicted, the replica set controller's next loop iteration notices the count is off and it creates a new one. Nobody had to write special crash recovery code. The control loop is the crash recovery code. There's a design choice underneath this that explains why it's so resilient. In engineering terms, Kubernetes is level-triggered, not edge-triggered. An edge-triggered system reacts to individual events, like a pod was just deleted, a node just failed. If it misses an event, it loses track. A level-triggered system doesn't care about what happened. It only cares about what's true right now. Why does this matter? Because if a controller crashes and misses 100 events, it doesn't matter. When it restarts, it reads the current state, sees the gap, and acts. It doesn't need to replay what it missed. Now, controllers do use events as efficient triggers. That's how they know when to wake up and check. But once triggered, they always read the full current state and reconcile from there. The current state is the source of truth, not the events. That's what makes the system so hard to break. Now, if this still feels abstract, that's fine. We haven't touched a real Kubernetes object yet. But from now on, every concept we cover is going to be a specific instance of this pattern. You'll see it in pods, in services, in deployments, and even in the scheduler. Same loop, different objects.
Let's start with the smallest unit. If you're coming from Docker, your first question about Kubernetes is probably, why do I need this extra abstraction? I already have containers. Why wrap them in a pod? It's a fair question, and the answer is not because Kubernetes is complex and likes layers. There's a real architectural reason. What might surprise you is that in practice, the most common Kubernetes use case is one container per pod. Not two, not three, one. So if most pods only have one container, why does the pod abstraction exist at all? Because Kubernetes needs an atomic unit to work with. A unit it can schedule onto a node, allocate CPU and memory to, health check, restart, and replace. That unit is the pod. It's the fundamental building block for everything else in the system. A deployment manages pods. The scheduler places pods. The kubelet runs pods. Everything operates at the pod level. The fact that a pod can hold multiple containers is a bonus, and it's useful when you need it. Your app server and its log shipping sidecar, your web server and a local caching proxy. These are tightly coupled helper processes that share a network and storage, and they make no sense running on different machines. Inside a pod, every container shares the same IP address. Container A can call container B on localhost. They see the same mounted files. From the perspective of the network, the whole pod is one logical host. Operationally, this is what matters most about pods. They're ephemeral. They are designed to be destroyed and recreated freely. They're not pets. You don't name them, nurse them back to health, or care which specific machine they run on. And if a container inside a pod crashes, the kubelet on that node will restart it. That's actually what crash loop backoff means. The kubelet keeps restarting a failing container with increasing delays. The pod itself stays on the same node with the same IP. But if the pod itself is deleted, evicted, or the node it's running on dies, that pod is gone. The replica set controller notices the count is off, and it creates a brand new pod. New identity, new IP address, possibly on a completely different node. This is intentional and by design, and it's the reason services exist. But we'll get there. You almost never create a pod directly. You create a deployment, which creates a replica set, which creates the pods. The control loop manages the lifecycle. You just declare what you want. Also, each pod gets a unique IP address within the cluster. No port mapping games, no collision worries. If you have 200 pods, you have 200 unique IPs. Kubernetes manages an internal flat network where every pod can reach every other pod by IP. And when you're curious to see what's actually happening with a pod, run kube-controlled describe pob and scroll to the events section at the bottom. It tells the full story. When the pod was scheduled, which node it landed on, whether the image pull succeeded, and why a container might be failing. Most debugging starts here. That's clean, but it creates a problem. If pods are ephemeral and get new IPs every time they're recreated, how does anything find them? You can't hard code an IP. The pod might be dead in 5 minutes. You can't predict the next IP. The scheduler might put the replacement on a totally different node. So how does your front end talk to your back end if the back end's address keeps changing? This is the problem that services solve. A service is a stable abstraction over a group of pods. It has a fixed IP address and a DNS name that never changes, no matter how many pods behind it are created or destroyed. When you create a service, you define a selector, a label query. Something like, give me all pods with the label app equals backend. The service continuously finds pods matching that selector, and it routes traffic to them. You might be thinking how the service knows which pods are alive. There's a controller, the endpoints controller, watching for pod changes.
When a new pod appears with matching labels, it gets added to the service's endpoint list. When a pod disappears, it gets removed. You don't reconfigure anything. It happens automatically. Now, there are different types of services, and it might be confusing. So let me walk through them quickly, because they actually build on each other. Cluster IP is the default. It gives your service an internal IP that's only reachable from within the cluster. If your front-end pods need to talk to your back-end pods, this is what you use. Nothing outside the cluster can touch it. But what if you need to reach the service from outside? That's where node port comes in. Node port does everything cluster IP does, but it also opens a specific port on every node in the cluster. Hit any node's IP on that port, and the traffic gets forwarded to the service. It works, but it's a bit raw. You're exposing node IPs directly, which isn't great for production. So on top of that, there's load balancer. It does everything node port does, but it also asks your cloud provider to spin up a real load balancer, an AWS ELB, a GCP load balancer, and point it at those node ports. Now you have a single, clean external IP. Each type builds on the one before it. They're layers, not alternatives. The reason this layering exists is that Kubernetes was designed to be infrastructure agnostic. Cluster IP works everywhere. Node port works everywhere. Load balancer needs a cloud provider integration. By separating the layers, the same service definition works in your local Minikube cluster and in production on AWS. The abstraction is the same, the underlying implementation changes. So to recap, pods are ephemeral and get new IPs constantly. Services give you a stable address that floats above that chaos. And when your service isn't routing traffic and you can't figure out why, run kubectl get endpoints and check if the list is empty. If it is, your label selectors don't match any running pods. 9 times out of 10, it's a typo in the selector or the pods have different labels than you think. This is one of the most common Kubernetes debugging dead ends, and doing this can help you some headache. Now the question becomes, who's managing these pods in the first place? A deployment is where you express your desired state for a workload. You're not writing a deploy script. You're writing a description of what should be true. I want 3 replicas. I want them running this container image. I want this much CPU and memory allocated. That's it. You hand this description to the API server, it gets stored in etcd, and the controllers go to work. But a deployment doesn't directly manage pods. It manages replica sets. A replica set is the thing that actually maintains the right number of pod replicas. The deployment sits above it and manages rollouts, the process of transitioning from one version to another. This separation is what makes zero-downtime deployments possible. When you update a deployment, say you change the image tag from v1 to v2, the deployment controller creates a new replica set for v2. It then gradually scales up the new replica set while scaling down the old one. This is a rolling update. At every point during the transition, you have pods serving traffic. Users see no downtime. If the new version starts crashing, the rollout stalls, new pods won't become ready. So the deployment controller won't continue scaling down the old ones. Your previous version keeps serving traffic. You can inspect what's failing, and if needed, you can run kubectl rollout undo to snap back to the previous replica set. That's why old replica sets aren't deleted immediately. They're kept around as rollback targets. By default, Kubernetes keeps the last 10 revision histories. Practically speaking, if a deployment isn't going the way you expected, kubectl rollout status tells you exactly where it's stuck, and kubectl rollout history shows you every revision and what changed. Between those 2 commands and kubectl describe on the failing pods, you can work through most rollout problems. So now we've seen how a deployment creates pods through replica sets. But there's a step we've been skipping over. When a new pod is created, it doesn't have a home yet. It's just an object in the API. Something needs to decide which node it runs on. When a new pod is created, it doesn't have a node yet. It sits in a pending state. This is where the scheduler comes in. The scheduler's job is very simple. Find the best node for this pod. Here's how it works. First, filtering. The scheduler eliminates nodes that can't possibly run the pod. Does the pod request 2 gigabytes of memory? Any node with less than 2 gigabytes available is out. Does the pod need a GPU? Nodes without GPUs are out. Does the pod have a node selector or affinity rule? Non-matching nodes are eliminated. After filtering, the scheduler scores the remaining nodes. It runs a set of priority functions. Which node would give the most balanced resource usage across the cluster? Which node already has the container image cached? Which node best satisfies the pod's soft preference rules? The highest scoring node wins. The scheduler tells the API server its decision by creating a binding object, essentially saying this pod belongs on node 3. And the API server then sets the node name field on the pod. And that's it. The scheduler's job is done. The scheduler is arguably the most complex decision maker in the cluster, and its entire output is one binding decision for one pod. Nothing else. The whole filtering and scoring pipeline funnels down to a single assignment. From there, the kubelet on that node, which is running its own control loop, watching for pods assigned to its node, picks it up, pulls the image, and starts the container. The scheduler doesn't deploy anything. It doesn't start any processes. It doesn't SSH into any machine. It makes a binding decision, and the API server handles the rest. The kubelet, doing its own reconciliation loop, takes it from there. No component talks directly to any other component. They all work through the API server.
This can help you with debugging. When you see a pod stuck in pending, run kubectl describe on it. The events section will tell you exactly what the scheduler couldn't find. Insufficient memory means your resource requests are too high for the available nodes. Didn't match node selector means your affinity rules are too restrictive. The scheduler is very specific about what went wrong. You just have to read the events. So far, everything we've talked about lives inside the cluster. Pods talk to services. Services route to pods. It's a clean internal network. But at some point, actual users on the actual internet need to reach your application. You could give each service its own load balancer, but that means a separate external IP and a separate cloud load balancer for every service you expose. That gets expensive and messy fast. You want one entry point that routes requests to the right place based on the URL. That's what Ingress does. An ingress is a routing rule set. You define host-based and path-based rules. It's essentially an HTTP reverse proxy configuration expressed as a Kubernetes object. An ingress resource on its own does nothing. It's just data in etcd. You need an ingress controller to actually implement the routing. An ingress controller is a pod running inside your cluster, usually Nginx, Traefik, or a cloud-specific implementation. It watches ingress resources, reads the routing rules, and configures its proxy to enforce them. Same pattern as everywhere else. Declare the what, a controller handles the how. Now let's put everything together. What happens when a real request comes in? A user hits api.example.com. DNS resolves to the external load balancer. The load balancer forwards the request into the cluster, where the ingress controller picks it up. The controller checks its routing rules. This host and path match the API service. It forwards the request to that service's cluster IP. The service looks at its endpoint list, maintained by the endpoint controller, and picks a healthy pod. The request reaches the container. The response travels back the same way. Every component we've covered in this video is in that chain. But what happens when something breaks? Node 3 goes down. The node controller detects the failure. The kubelet has stopped sending heartbeats. After about 40 seconds, it marks the node as unreachable and applies an unreachable taint. The endpoint slice controller acts quickly. It removes the unreachable pods from the service's endpoints. Traffic stops going to a dead node. This happens well before the pods are formally replaced. Then, after a toleration period, 5 minutes by default, the taint-based eviction kicks in, and the pods are formally evicted. The replica set controller notices the count is off and creates a replacement. The scheduler picks a healthy node. The kubelet starts the container. The endpoint slice controller adds the new pod to the service. Traffic flows again. The whole system recovers.
During all this, no single component orchestrated that recovery. No master process told the system what to do. 5 independent controllers, each following its own simple loop, collectively healed the system. A quick note on where this is headed. Ingress is being gradually succeeded by the Gateway API, which supports more advanced routing, like traffic splitting and header-based matching. If you're starting a new project, it's worth looking at. The architectural pattern is the same. Declare routing rules, a controller reconciles them. Let's zoom out. Kubernetes is not a deployment tool. It's a reconciliation engine. You declare what should be true, and a set of independent control loops work continuously to make it so. Pods exist because some containers need to share a network and storage. Services exist because pods are ephemeral and you need stable addresses. Deployments exist because you need safe, reversible rollouts. The scheduler decides where things run, and Ingress brings the outside world in. Every one of those is the same pattern: desired state in, reconciliation running, reality converging. That's the whole machine. If this was helpful, please like and share. Thanks for watching, and see you in the next one.